presentation tomorrow. Uh, just a tiny talk I have to do in front of professors and in front of my professor, my colleagues, and uh, and I have to apparently talk about. That's what I told them about this thing called block diagonalization. And I searched it a lot. Searched a lot about this. There is something called Jordan form, and I don't know what not. But in quantum mechanics, this thing is just as real as unicorns. Nothing like this exists. Nope. But there is no such algorithm which will tell you to form a matrix into blocks in quantum mechanics. I don't think it will be even useful because most of the matrices we deal with are Hermitian, and Jordan forms are used when your matrix is not diagonalizable, but as long as you have you have a Hermitian matrix, it is always 100% diagonalizable. So I don't know what was I searching up, and I don't know where all I landed, but in this journey of trying to find this thing, whatever this was, whatever I was trying to do, I don't know what I was doing anymore, but I learned some stuff, and I want to just do a rehearsal so that I can present the same thing tomorrow with in in such a way that people understand, and they they feel that they at least they got to know something, or it was worth knowing. So I will. So even though I don't know what is this block diagonalization, there is something else called the block diagonal matrix, or I would say block diagonal form. We have so many names. Another name is irreducible representation. Too many mosquitoes around me. Representation of rotation matrix. Rotation matrix. So now let us see what all we can do. So first of all, we want to understand rotations, what rotations are really like in quantum mechanics. And quantum mechanics there is no such thing as absolute motion, so even rotation there might be no such thing as absolute rotation, but we still want to learn, understand, see quantum mechanics in analogy of rotations, which we have in our everyday world. So first of all, to understand rotations, suppose you have some 3D object initially, something like this, and after some time, I don't know, something happened to this and its orientation changed. So it maybe I think I can do it. uh, let's say oh, I can do that, yeah. I will just copy this thing, and okay, I got another copy, very good, and I can just rotate this up, very nice. I just rotated this thing, and this thing got rotated, though the origin is at the same place. Now let me change the axis now. Okay, I think it's good to keep this old axis. So relative to my old axis, I can see a change now. The red one is the old one I had. Initially, I had this initially uh, this axis. I'm just drawing it, and this thing just rotated. And to describe this rotation, like before and after, we have something called Euler angles. And Euler angles, even in Euler angles, different people use different ways, different methods, and different notations. And I will use z, y, z notation. So basically, how this Euler angles work is, suppose you have this 3D system, and I want to uh, describe a rotation alpha, beta, gamma in Euler form, in Euler angles. First, what I have to do is I have to see this alpha, and I have to rotate this alpha. I have to rotate this space about the z-axis uh, with angle alpha. So it will be somewhat rotated like this. It will somewhat get rotated like this. Now this new rotated coordinate system, so as you can see, like z-axis will remain as it is, but now x will become x prime, y will become y prime. My x and y axis got shifted, but z is just as there is. Then after you do this, uh, you now take beta. uh, you now take the y axis. You take the y axis, and now about this y axis, okay, the new y axis you have, you take this new y axis you have, and now about this y axis you rotate it again. So this will remain as it is because you are rotating about this axis, and now you have to rotate an angle beta. So it will be something like this. uh, it will be something like this. uh, so even the z axis will get rotated beta, beta. And then once you do that, so what will happen is z will become z prime, y prime will remain y prime, and x prime will uh, become x double prime, right? And x got changed. Now finally what you do, again you come to this now what you do. Okay, I have to recheck if this is what the convention they are using, or else it won't be a good idea. So Euler notation, let me check it up. Hmm. Yeah, that's what they are doing. So yeah, and then okay, I'm not going wrong here. Then again about the z prime, you do the rotation again, x will change, x and y will change. So let me use another color here. So many colors. I don't know why this much complicated, but that's how they do it. So now this will be gamma. Okay, this doesn't even look neat now. So basically, you had your space, you had your space. You first do a rotation about z-axis, with some angle alpha. Then you do rotation about y-axis, not y-axis, y prime axis, with some angle beta, and then finally you do a rotation about z prime about angle gamma, z double prime. So the axis totally get changed here. Like initially, suppose if you had xyz coordinates, Now in this new coordinate system, x prime and y prime, because you did a rotation, x axis got changed, and then after I have to write here, I think, yeah. And then again you did about the y prime, so you have now x double prime, x double prime, y prime, z prime, and again you do about the z axis, about the, okay, not z double prime, just z prime. And what you get is a new space where you have x prime, x triple prime, just some new coordinate, y double prime, and z prime. So this is what Euler angles. So basically, you had space, you did a rotation uh, in Euler angles convention as alpha, beta, gamma, and you have some uh, disoriented object. Initially, you had object aligned with your perpendicular axis, and you did some Euler angle transformation, and it just went uh, to it is still the same object, but you just disoriented it. And to describe this, we can easily describe this because we know that a rotation uh, a rotation about z axis is we have a matrix for this, right? A rotation about z axis, like for alpha, let's say about the z axis we have to do an angle alpha rotation. So this will be something like this matrix looks something like this, if you have seen. Okay. Cos alpha, cos alpha, sin alpha, and minus sin alpha. Fine. So what will this do in a 3D space? Initially, if this was like this, xyz, if I apply this matrix on this space, it will keep the z axis intact, and it will just do a tiny rotation angle alpha. Actually, you can do as many you can extend alpha as much as you want, not necessarily uh, infinitesimal, because this is an exact operation, no approximations. So similarly, we have a rotation matrix for x with some beta, and also for y with some gamma. So we have these three. So if you have your space, if you have some state alpha, so basically some space, some object, what you have to do, you have to first rotate, we first rotate this about uh, the z axis with some angle. Okay, 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 I messed up. Okay, fine, fine, fine. Let me just say psi, why not, because psi is everywhere. So uh, okay, I don't even want to use psi. What can I use? What if I just leave it as x, some state x, it can be anything. Okay, no, what am I doing? You may confuse it for x axis, a vector v, take it or leave it. So now, then what I have to do is I have to now rotate, I have to rotate this about the new y-axis I had with angle beta, and then finally I have to rotate this about the new z-axis I have about angle gamma. So this matrix immediately we easily know this matrix. We have it is with respect to our coordinates, but these two are not with respect to our coordinates. When we are applying this we are applying this on the rotated system, so we have to first find a way to uh, represent this in r space, and we can easily do that. So what we can do is, so this first of all we will go step by step. We know what will it be in what will a beta rotation look like about y-axis in r space, uh, but we have to find out what would it be in his space. So we just do a similarity transformation. So how we do that is, we first come back to this operator only works in r space, not in the rotated space. So what we do is we come back from that guy's space, uh, we come back from this space, we take inverse of it, alpha, and then we rotate, then we rotate with respect to y axis, and then pretend nothing happened and just put back beta. So this rotation will correspond to this. Now so what would it be? So r y prime beta, uh, and okay, I have substituted it, right? I have rz of beta, ry of beta, okay, beta not beta, sorry, it was alpha, right? rz of alpha, rz of alpha, rz inverse of alpha, and rz of alpha, okay, here also alpha, and then we have rz of alpha, and then finally the state. So these are inverses of each other, and now we have this. So our we have our rotation matrices in terms of our coordinates, almost all of them except this guy. We do the same thing. We first take inverse of we do the same thing, assume that this is some rotation capital R. So this r z prime gamma will, we do a similarity transformation again. We pretend that we first find out how will this look like in r space. uh, so this rotation, this whole rotation we will first convert back to our space by just doing r inverse, and then after doing this rotation we bring it back to our space, pretending nothing happened. And so uh, what is this? So this will give us r of gamma and r z of gamma, and since this and this inverse cancel each other, you just have x. So basically you will get r of alpha, r of beta, r of gamma. So r of gamma, so this is x. So basically a rotation, an Euler rotation, alpha beta gamma on our space with whatever rules we set initially can be written as R of alpha. Oh, also not to forget this. Oh, yeah, yeah. This is Z, this is Z, and this is Y. Y sandwich between Z. And why have we chose this specific notation? It will come later, so we will see it. Rz of alpha, Ry of beta, Rz of gamma of x. This is first result. Now, next, what is there in the book? Hmm. So, so we can actually represent rotations in terms of exponentials, and depending on what dimension we have, 2 cross 2, 3 cross 3, like we have different ways to represent rotations. And one of the ways is, if I want to rotate if you want to rotate something uh, with respect to z axis with some angle alpha, you can just apply this operator sigma z. These are polymatrices of alpha, and this will work. uh, I don't know what are the limitations of this, but similarly, if you want to do a rotation about any I of ith axis with angle theta, you can just apply this operator. Sigma I is the polymetrics, and alpha, some theta angle. So if we want to show it in terms of whatever we did in terms of Euler angles, it would look something like this. Let's do it. So let's do it. So in terms of Euler angles, like we said, an Euler rotation, d of alpha gamma beta, alpha beta gamma, will look like, uh, as we said, dz of alpha, d, what is next, y of beta, and again dz of gamma. And now we can write this as e power minus I by h cut polymatrix z of alpha. uh, Let me write in terms of exponent. No, I can, let's just keep it as this is an operator, not to confuse. And times this e power minus I by h cut sigma y beta, and finally e power minus I by h cut sigma z of gamma. So this is how it will look in terms of exponential operators as rotation operators. And what else is this? So what else do we have here? Let me see. So I have to also now. Uh, so I don't want to do it, but what is happening? So basically, I don't want to do it, but but I will still tell. So find the eigenvectors of this matrix, eigenvectors of polymatrix e power, I mean sigma 3, then diagonalize it, and then just calculate this matrix, then you calculate this matrix, you calculate this matrix. After all the calculation, this is what you get. I don't know. I don't think I will show this in the presentation. This part, I can at least not the calculation. I will just go to the result if I want to. And so let's go next. So now, what he's trying to show is the matrix in the middle is purely real. Okay, I think he's trying to force me to calculate. So I think I can't resist now. Let's calculate. Oh man, I'm so sigma 1, sigma 2, sigma 3, polymatrices. So sigma 1 is not necessary, so it is something I don't care right now. Sigma 2 and sigma 3. Here we go. Okay. So this is 1 minus 1 0 0. Or did I saw it wrong? No, it's correct. 0 1 1 minus I. What was it? Minus I 0. 0 minus I 0. And this is not necessary. So let me just calculate these values. So so what will be e power minus I by h cut plus or minus something. So let's keep minus, then I will flip the signs. uh, Sigma 3 times alpha. So this will be so first of all, eigenvalues of this are plus or what are eigenvalues of this? Plus minus 1, 1 and minus 1. And eigenvectors of this are, let me check, 1 0 a b. This gives me a b back. So this will give me, so one of the eigenvector is 1 minus 1, and the other vector is this is very torturing. The other eigenvector will be, let's see, 1 0 0 minus 1 a b minus a minus b, a equals to minus a minus b equals to minus b. What did I just do? And so I have okay, I feel too stupid now. This implies that a equals to 0. This implies that b can be anything. Same thing happened above here. uh, b must be equal to 0, and it can be anything. And this is already diagonalized actually. Uh, so this means uh, this can be diagonalized something like this. It is just identities around here. And here I have to just write e power I by h cut times first eigenvalue and second eigenvalue. So let me write lambda here on the top. Lambda is 1, and so it will be beta 1 times beta and e power minus I by h cut times beta. I hope I did it right. Oh, it's alpha. Okay, fine. Alpha, no problem. Alpha, alpha. And plus minus, it doesn't matter where you keep it. I think I will just keep it as it is. Same thing will be happening here, but same thing will be happening for this matrix, because so this will be like something like this: I by h cut beta minus I by h cut beta, and the tough part will be this one. Let's calculate that and keep going. What is this again? 0 I minus I 0. So the first eigenvector, so it is hmm, minus I times b is a, and a times I is b. So you can just write something like this. This is your first eigenvector. Let's find the other one. The other equation you get is just by flipping signs. Just flip the signs, and so if you flip the sign, what you would get is minus b, and you get I times b as I times a, actually I times a as minus b. Okay, sorry, it is minus a. Am I really? What am I doing? Okay, I messed it all up. Just I thought I just flipped the signs, so I will just do it again. Minus I times a minus b minus I times b. Minus I times b is a minus a, and I times a is minus b. So I can just conclude that a is I times b. So my eigenvector will be I and 1. So I got my eigenvectors. Let's do it now. 1 I1, of course normalizing them. 1 I1, and you have this e power I beta by h cut e power minus I beta by h cut, and then oh, also this is gamma for z, gamma gamma, and so Oh yeah, also this should be inverse of this. This is a long calculation. I don't want to do it, but let me just use a software for at least calculating the inverse. Should I do that or should I not? I think I should. So let's call this P. Why am I not going inside? So the first entry was what was it? 1, and the next entry in the row is I. Similarly, here I'm gonna write, and I will just invert this. Let's call this matrix, I don't know, Q. I successfully inverted them. Let's whatever was the matrix inside at the center, let's write that as well. Let's call it C. So it was plus minus here and there, it's okay. So it will be percentage e power, I will take h cut to be 1 for simplicity, percentage I times, I can't take I1 so now it will be angle beta, right? B, and then close, comma 0, and same thing I copy. Okay, I just write it down, 0 comma, if I can copy, why not copy, but I have to be careful with the sign. So let me copy, paste. So here we go. Oh, come on. Where did I miss the... Okay, I fixed it. And now finally I have to just do that thing. So it will be P times C times Q. And I just expand this. Okay, I will just... so actually if you look carefully, you will see that all these values, all these entries will be real. For example, let me call this matrix result as R, and I will show you that the image part of this is imaginary part of this is 0. You see, it only has real part, that's a good thing. So that's what we get. So what is it again? Cos, sine minus sine. Let me write this down. Half of cos beta sine beta minus sine beta. So yeah, we did it. So we get this in the end. So what is the purpose of all this? So they want to stick to this convention for some reason. Hmm. Hmm. I don't know what he means by this, but so this thing we found. Okay, so I want to just paste it. This is very important. This thing we found. So where did we were calculating somewhere, right? Yeah. This is called irreducible representation. Representation. J half. In J half, we have irreducible representations for different J's, and this matrix is denoted by. Oh no, no shit. No problem. Let me go back. I have to find the book again. So yeah, this is denoted by d half dash dash alpha beta gamma rotation. So what is so significant about this? I don't know. Maybe I will figure out soon. And then what is discussed about all this later is then he just goes in representations and all that. Hmm. Representations of rotation operator. He wrote something like this. The very reason is that what we did before can be done in this way. So since we know that any rotation can be split in terms of alpha, beta, gamma, we get something like this. This is an important result. Hmm. So what we have is I don't know what do we call this matrix. Mm, okay, let me just stop end this for now. Thank you whoever watched this. I don't know why did you did, but